Okay, here's a lesson on general rational functions. They're going to be a little more involved than the quote-unquote simple rational functions from 8.2. This will cover pretty much any rational function you see. Alright, so our first goal is to find the domain and then eventually be able to find the ranges of the function. Okay. After that, we're going to graph rational functions. Because we're able to find the horizontal or oblique asymptotes. And we'll talk about what oblique means, basically diagonal. And then we'll find vertical asymptotes. And being able to do these two things will allow us to graph all rational functions. Okay? So first here we're going to find domain, just practicing with that. And domain is all about two questions. The first question being, can I divide by 0? Can I divide by 0? And the second question is, can I ever square root a negative? Okay. So what I'm saying is if those two things are ever possible, whatever makes these things happen is not in our domain, and everything else is. So looking at this first equation here, our rational function 2x squared minus 4 over x plus 5, I'm looking for two things. I'm looking for variables in the denominator, and I'm looking for a square root. Because if you ever square root a negative, you end up with an imaginary number. So it can't be in our domain of real numbers. Alright, so we always start out with all real numbers, and then basically we're going to describe what real numbers would cause one of these two things above here to happen. In our first function here, there's no square roots, and in fact, in all of these functions, there are no square roots, so we don't have to worry about that. But there are denominators, and in those denominators are variables. So right here, we've got an x involved. And what we want to know is, when could x possibly make this entire thing 0 in the denominator? So I learned that by setting whatever the denominator is equal to 0 and solving for the x that creates that scenario. So then x would equal negative 5, because I would subtract 5 over on both sides. Well, knowing that x equals negative 5 creates 0 in the denominator, I can then say that our domain is all real, provided that x doesn't equal negative 5. Because as long as it never equals negative 5, we will always get an answer out. Okay? So that would be my domain for this first equation. Second one here, I do the same thing. X squared minus 4 equals 0. X squared then equals 4 when I add 4 to both sides. And when I square root, okay, I get x equals positive or negative 2, which means that we're all real except x can't equal positive or negative 2. Alright? Now in this one here, it's a little trickier, because when you get x squared plus 1, you set it equal to 0. So you get x squared equal to negative 1. Square root, uh-oh. I've got x equals plus or minus I, an imaginary number. What that means is that there's no real number that you could plug in here that turns our denominator equal to 0. So then our domain is just all real numbers. Alright? Same thing here. There is no variable in the denominator. There's no x, there's no y, there's nothing. There's just a constant of 3. So there's nothing, like 3 could never equal 0. Ever. So again, all real numbers is my domain. And then lastly, just a quick one, x minus 1 equals 0, so x equals 1. So x can't equal 1. Alright? And this is going to lead into other ideas, but it's an important skill. Okay? Okay, so the skill that I'm referring to is vertical asymptotes. The way you find vertical asymptotes is almost the exact same way you find the domain of a rational function. You take your denominator, you set it equal to 0, and you solve. So you get x squared equals 4. X then equals plus or minus 2, just like in the problem before. And what that tells me is that I have a vertical asymptote at x equals 2 and x equals negative 2. Remember, the equation of a vertical line is x equals some constant, because the y will never change. The y will always be changing, and the x will never change. The x will always be 2, no matter what. So, we have our vertical asymptotes. For this one here, we set x minus 1 equals 0. We get x equals 1. So that's our vertical asymptote. Again, vertical asymptotes are the visual image of an undefined number. Okay? Here we got x squared plus 4x minus 21 equals 0. So I'm going to factor. I get x plus 7 times x minus 3 equals 0. So I take x plus 7, set it equal to 0, and x minus 3, set it equal to 0. And I get x equals negative 7. And then I get x equals 3. So I'm going to have 2 vertical asymptotes, which is fine. You could have 3, depending on what kind of function you have. Alright? You could have 4. You could have as many as are undefined numbers. Alright. X squared plus 1. We had this in the previous slide. X squared then equals negative 1. So x equals plus or minus I. And again, we can't get a real number to make our denominator 0, so there would be no asymptotes, no vertical asymptotes. Alright, so here we come to a key concept, finding our horizontal asymptote. Alright, so our rational functions, we say let p of x and q of x be polynomials with no common factors other than plus or minus 1. Which means they don't simplify, or we have simplified the rational function as far as we can go, which is an important step, and we'll talk about that some more later. But looking at our two functions here, the x-intercepts of the graph are the zeros of your numerator. If you think about it, when you find your x-intercepts anyhow, you set whatever you're working with equal to 0 and solve. The first step in doing so would be to multiply both sides by your denominator, which eliminates this denominator anyways. And so all you're doing is kind of a shortcut by setting your numerator equal to 0. Okay? And then you solve, and whatever makes your numerator 0 makes the entire thing 0, because the numerator had to be 0. The denominator never can be. Alright? So that's our first important concept. So let's make sure we have all of this data in our notebooks. Okay. The second important fact, our vertical asymptotes, which we've been talking about, are the zeros of our denominator. Whatever makes our denominator 0 is undefined and creates a vertical asymptote. We've talked about that. So that's a key concept to continually go back to. Alright, the graph of this function has at most one horizontal asymptote, or what we call an oblique asymptote, which is diagonal. Okay? And it's all based off of the power or degree of our two functions. Okay? So you notice here, we have a degree of m for the top one. M is in mother. And we have a degree of n. N is in Nancy. Right here for our denominator. Okay, so you're looking at this as, is this degree here less than, equal to, or greater than the denominator's degree? So if the numerator has a lower degree than the denominator, then y equals 0 is your horizontal asymptote. If they're the same power, then you just look at the coefficients and you get your horizontal asymptote. If the numerator's power is greater than the denominator's, then what you have is an oblique asymptote. Your job will be to perform long division and then determine the oblique or diagonal asymptote that will show up as an equation of a line. Okay? One important note that may not make sense at the moment, but when you do long division, sometimes you end up with a remainder. And as x approaches infinity, or x gets really, really big or really, really negative, the remainder will disappear. It approaches 0. Basically, you ignore it. Okay, so you don't have to worry about whatever remainder comes out. All right, it's kind of a strange concept. Basically, it has to do with the way the ratio works as x gets really big, and we'll talk about that. Okay, and it's all about patterns, really. So here's an example of a scenario where our power is larger on top than on bottom. Okay, the degree of the top, m, equals 4, and n in the denominator equals 3. Okay, so m is greater than n, and we need to do long division. So here's a little refresher in long division. We're going to take 3x to the 4th plus 0x cubed minus x squared plus 0x plus 0. I'm just putting in, these 0x's as placeholders so that I make sure that I get the complete division. Got to do the same thing for my function in the denominator here, x cubed minus x squared plus 0x plus 1. Alright, so then I say, alright, well, 3x to the 4th divided by x cubed is what? It's going to be 3x. Because if I took 3x times x cubed, I get 3x to the 4th. Okay, so then when I multiply 3x times x cubed, like I said, I get 3x to the 4th, but then I have to distribute it to all 4 parts. And I get minus 3x cubed plus 0x squared plus 3x. See, I'm trying to keep everything organized. X squareds over x squareds, x cubes over x cubes, and so on. Then I subtract, putting parentheses around the entire thing. And those parentheses help me to make sure that I distribute this negative symbol here to all 4 parts. So we get 0 there, 3x cubed, minus x squared, and minus 3x. Alright, so then I say, what's 3x cubed divided by x cubed? Well, that's plus 3. Then we get 3x cubed minus 3x squared plus 0x plus 3. And we got to bring down the 0. Alright, subtract. I get 0 here, 2x squared minus 3x minus 3. Alright, so at this point, here's where some of the weird stuff starts to happen. I'm going to erase, get a little room up here, and I'm going to write my full answer. Alright, erase, cleaning up some stuff here. So, my answer is 3x plus 3 plus 2x squared minus 3x minus 3 all over x cubed minus 2x squared plus 1. The reason I'm done is because 2x squared can't be divided by x cubed evenly. It would just stay the same. And so we know that this bit, once that happens, this bit becomes the remainder. Okay? And this is what I was talking about earlier. This remainder, functionally for us, means nothing in terms of the way our graph looks. What happens is as x gets really, really big, so let's say you plugged in 1,000,000 for x, this denominator gets bigger so much faster because it's got a higher power at this point that it approaches 0. Because when your denominator's, infinitely larger than your numerator, we say that you're approaching 0. And so functionally for us, we ignore it. We don't even have to worry about it. But our asymptote is represented right here, 3x plus 3. So if I were to draw that, I'd have, my x and y axes, and I'd go up to 3, 2, 3, and then I would, plot a point, go up 1, 2, 3, over 1, 1, 2, 3, over 1. And I'd have a line with a slope of 3 and a y-intercept of 3, 0, 3. That represents an oblique asymptote. So we would write that as y equals 3x plus 3. Okay? It could be y equals x. You know, it just depends on what your division creates for you. All right? But that's how it looks. All right. Okay, we want to find horizontal and oblique asymptotes again. And we're going to look again to the power of the function. So our powers are the same here. M equals n. And I usually make a note of that. You know, I'm trying to organize my work. If I don't organize my work, it's hard for me to go back and look and say, well, what did I do wrong? All right? M equals n here. So I know that y equals a over b. And a over b in this case are 8 over 4. The coefficients in front of our functions, which equals 2. So our horizontal asymptote's at y equals 2 now, instead of y equals 0. Okay, our next example, we have another one of those where the power on top is greater than the power on the bottom. And this one's a little funky because it's going to create an x squared oblique asymptote. Okay, and I just want to show you that this can happen, but it doesn't necessarily change the way we do anything. Okay, so again, we're going to long divide because the power on top's greater. So we got 2x to the 5th plus 0x to the 4th minus x cubed plus 0x squared plus 0x plus 2. Okay, then we got x cubed plus 0x squared plus 0x minus 1. Alright, so 2x to the 5th divided by x cubed is 2x squared. When we multiply through, we get 2x to the 5th plus 0x to the 4th plus 0x cubed minus 2x squared. And all I did was distribute this to here, 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 and here. Alright, so I get 0, 0, negative x cubed, and positive 2x squared. So then I say, well, negative x cubed divided by x cubed is minus 1, and we get then we get x cubed negative minus 0x squared minus 0x plus 1. We bring down our plus 0x and our plus 2. So then we end up with 2 minus a 1. We get zeros going around. We got 2x squared plus 1. So our final answer is plus 2x squared plus 1 over x cubed minus 1. Again, this disappears, and your answer for your oblique asymptote is 2x squared minus 1. We will most likely not be graphing anything involving oblique asymptotes of a higher degree than 1. So, you know, you won't have to worry about graphing something like this. I just wanted to show you that it was possible and that your procedure was ultimately the same. Okay? Alright, so here's a nice and easy one. We want to find the horizontal asymptotes, and we look and say, well, this power is a 1, because that exponent above the x is 1, and this power is a 2. So m is less than n, and by our rules, that means y equals 0 is the horizontal asymptote. Boom. Okay? Which is like the simpler, quote-unquote, simpler rational functions we had the other night, where it was like a constant over x minus 2. Again, that power we say here is a 0 power, and here is a 1. So again, y equaled 0 was our horizontal asymptote, and then we were talking about h and k because if you had a little k value out here, like a 1, then y equaled 1 became your horizontal asymptote. Alright? But for most of our general rational functions that are a little more complicated, we're probably not going to have much added out here as a k value. But if you do, you know what to do with it. Alright? It shifts your horizontal, or your horizontal asymptote vertically. Okay, so steps for graphing a rational function. I would make sure that I have this somewhere nice and neat. All these steps, because this is kind of what I want to see. Alright, I'm asking you to find the domain of the function. Then I'm asking you to write the function in lowest terms. And what that means is we're going to factor the top and bottom. And then simplify if possible. We're going to find vertical asymptotes by finding the zeros of the denominator, which we talked about earlier. We're going to find the horizontal asymptotes, which we just spent a lot of time working on. And then we're going to enter the function in our calculator and graph the function there. You can go to the table in your graphing calculator, and you're going to create an x and y table on your paper that you fill in based on this. Okay? You don't have to evaluate, a whole bunch of points. Then I want you to graph your asymptotes and label them. Okay? So you're going to use dashed lines, and you're going to graph your asymptotes. And then you're going to plot the points that you used in your x and y chart and make sure you're nice and neat there. Okay? The other thing I want to make sure that you guys do is always have your x-intercepts and y-intercepts. All right? That way you're nice and anchored. Okay? Plus those are easy ones to find usually. Alright, so example 1 here. This function in lowest terms, well, the numerator can't be factored any further, so it stays the same. But our denominator is a difference of 2 squares, so I can say x minus 2, x plus 2. It's factored. That's in lowest terms. If it could cancel, then I would. Okay, let's say it was x minus 1 on the top, I would cancel, and away I go. And it'd just be 1 over x plus 2. But this can't cancel, so we're good. Again, our domain, we set our denominator equal to 0 and solve. And I get x squared equals 4, so x equals plus or minus 2. So my domain would be x, all x's, provided that x doesn't equal plus or minus 2. To find my x-intercepts, I take my numerator, x minus 1, and I set it equal to 0, and I get x equals 1. So at x equals 1, we have the x-intercepts, 1, 0. So there's only 1. My y-intercept is the same for every other function in the world. The process to do that is you plug in x equals 0. So I go 0 minus 1 over 0 squared minus 4. And I should get 1/4. So then 0, 1/4 is my y-intercept. Right? So from that, I can say my vertical asymptotes come from the domain. So we have one at x equals 2 and x equals negative 2. My horizontal asymptote, the power of my numerator is 1, the power of my denominator is 2, so m is less than n, so y equals 0 is my horizontal asymptote. Okay? Okay, so next is our entering this in the graph, in our graphing calculator. It's really important that when you go to the y equals part, you make sure you use parentheses. So I'm going to have parenthesis x minus 1 divided by parenthesis x squared minus 4. Okay? We got to make sure that we keep PEMDAS in mind, which is why we use parentheses. Alright? So then we hit enter and we graph, and then you go to table. Alright? Table is second graph, and if you're having trouble seeing things, or maybe it's giving you like every 30th point, like 0, 30, 60 as an x value or whatever, you can always go to second window, and that'll be your table setup, and there will be a change of table, and you want to make that 1 or maybe 1/2, something in there. And you want to start at whatever you're starting at. So I'm starting at -5. There's a table start. You can change that to -5. Okay? If you go back to graph, you can look at the shape and get a good idea of how this thing's going to function. Okay? And then go back to your table and fill in here. So at -5, we should get negative 0.28. Oops, let me get my pen back here. 0.28. At -4, we should have negative 0.42. At -3, we should be at negative 0.8. And you'll notice at -2, you have an error. Hopefully that makes sense, because at -2, we have an asymptote, which means we have an undefined number, which means we have an error. Okay? Let's see. As we keep going down, at -1, we're at 0.67. At 0, which we already know, we got 1/4, or 0.25. At 1, we're at 0, which we already knew from our x-intercepts. And at 2, again, error. Okay, that's where our asymptotes lie, 2 and -2. At 3, you're at 0.4. And then at 4, you're at 0.25. And then at 5, you're at 0.19. Okay? Alright, so these are the points we got. Okay, now we want to go ahead and be armed with our information. We have vertical asymptotes at -2 and 2. So I'm going to space this out a little bit so it's easier to see. And I'm going to use every other grid as one unit. Alright? You know, you can always do this. It helps kind of make things a little nice and neat. Alright? Alright, so at -2, I'm going to use red for my asymptotes. We're right there. And at 2. And I label x equals 2, x equals -2. Alright. We have a horizontal asymptote at x equals 0. And there we go. And then we just plot our points. At -5, we're at -0.28. Oops, let me get my pen back. And then at -4, we're at 0.42, then -0.8. And you can see from your graphing calculator that the graph on this side travels something like that. It stays really, really close to the asymptotes towards the end. Alright? And then we're going to plot the points in between. At -1, we're at 0.67. At 0, we were at 0.25. And at 1, we were at 0. And so this brings up kind of an important, strange concept for you guys. Oops, sorry, that didn't quite go through the lines, but there you go. This should be going down more like that. There you go. Alright, so here's kind of a strange scenario. We cross our horizontal asymptote. And you're probably used to the idea that you can't cross an asymptote. And, most of the time with our vertical asymptotes, that's true. Vertical asymptotes are the visual representation of undefined numbers. 2 and -2 are undefined, so we can never actually touch them. But a horizontal asymptote is a pattern. A pattern of the end behavior of our function. Okay? And what that means is our function will approach this number, but it won't, reach it as the function ends. And so over here on this side, we're going to end up looking just like this. And again, the end behavior of our function right in here. As it ends, it gets really, really close but never actually touches. As this ends, we get really, really close but never actually touch it. The arrows that point off to what we call negative infinity and infinity represent the end behavior of our function. And they're patterned to get close to x equals 0, or excuse me, y equals 0 in this case, y equals 0. Alright? But that doesn't mean that in the middle we can't cross it. So there's nothing wrong with that. So our oblique and horizontal asymptotes we can cross, but our verticals we can't. Alright? Okay. Here we got one. Our top is already in lowest terms, so 3x squared. And our bottom we need to factor to x plus 4 times x minus 3. Alright? So our domain is by setting our denominator equal to 0 and solving. You get x equals negative 4 and 3. Which means we can't equal negative 4 or 3. Our x-intercepts are going to be whatever makes this top 0, which is just going to be 0 and 0. Which means that our y-intercept is going to be the same. Because if I plug in 0 for x, I get 3 times 0 squared over 0 plus 4 times 0 plus 3. So our top ends up equaling 0 over 12, which is 0. Okay. Our vertical asymptotes, again, come from our domain. We're going to have one at x equals negative 4 and x equals 3. And then we look at our powers to find our horizontal. They're the same. So we use the coefficients, y equals 3 over 1, or just y equals 3. Alright, so then we enter this thing into our calculator. And again, we want to make sure we have parentheses. 3x squared divided by x squared plus x minus 12. And then you can hit graph and see the picture. Okay? The other thing you can do is go to your table, set it up, make sure you start at negative 5. You can start wherever you want, but I'm just giving you guys a good balance. You get some negatives, you get some positives, you get an image, and go from there. Okay, so at negative 5 I got 9.38. Alright, at negative 4 I got an error, which makes sense because remember our vertical asymptote, undefined, negative 4. At negative 3 I'm at negative 4.5. At negative 2, I'm at negative 1.2, and negative 1, I'm at negative 0.25. And then at 0, we got 0, 0 as our vertical, or as our x and y intercept. At 1, I'm at negative 0.3, and let's see, at 2, I'm at negative 2, and then at 3, I've got an error again, because that's where our vertical asymptotes sit. At 4, I'm at 6, and at 5, I'm at 4.2. Alright. So, we're going to go plot those points and draw our vertical and horizontal asymptotes. Okay, so our graph here, our vertical asymptotes are at negative 4. I'm going to use the actual grid lines this time. And actually, I'm going to make the asymptotes red, like last time. So x equals negative 4. X equals 3. So then we need to go up to y equals 3 and put together our horizontal. Oops, that's 4. Okay, and we get y equals 3, our horizontal asymptote. And then we can plot our points. So at negative 5 we're at 9.3, so we're up here. Okay. And I'm actually looking back at my table on my calculator now, and I'm looking for more points that are to the left of this asymptote, because you always want to get some that are in between, to the right and to the left, and I'm thinking that we didn't pick enough that were to the left, because I've only got 1 point so far. So at -6, I notice that I'm at 6. All right. Then at -7, I'm at 4.9. So we're just under 5. And then I look at my graph picture, and it looks like it comes down, sweeps through these points, and heads on to approach 3. All right. All right. So then we want to plot the rest of our points. Okay, so at -3, we're at -4.5, right around there. At -2, we're at -1.2. At -1, we're at -0.25. And at 0, we're at 0. And then at 1, we're at -0.3. And at 2, we're at -2. And then again, we have our asymptote at 3. So it looks like it just creates sort of a parabola heading down. Alright, and then at 3 we have our asymptote, and then at 4 we're at 6. And at 5 we're at 4.2. Right around there. And you might pick another couple points if you're having trouble seeing the value. So at 6, I'm at 3.6. You know, you really want to get a good pattern. And that's what I want to see. I want to see nice, organized, neat work. Okay? Alright, there's your graph. So the red won't show up, right? You look at your graph, you know, the red doesn't show up, but it's there. It's a pattern. It's affecting the behavior of your graph. Okay? Alright, here is our last one. It's going to be a little trickier. We want to factor the top to create lowest terms. So we're going to say x minus 3 times x plus 1 over x plus 4. Alright, that's in lowest terms now. Our domain is going to be based on our denominator, so x can't equal -4. X provided that x can't equal -4. Our x-intercepts are going to be whatever makes the top 0. So it looks to me like 3, 0, and -1, 0 would make the top equal to 0. Our y-intercept are going to be whatever when we plug in 0 for x. So if I plug in 0 minus 3 times 0 plus 1 all over 0 plus 4, I get -3 over 4, or a 0 and -0.75. However you want to write it. It could be 0, just like that. Okay. Our vertical asymptote comes from our denominator again, right here, this guy. And we get x equals -4. Okay, and then our horizontal asymptote, well, we got to do some work here. We're going to have to do long division. Alright, so we're going to take x squared minus 2x minus 3 and divide by x plus 4. X goes into x squared, x times x is x squared plus 4x. And then we subtract. So we get -6x minus 3, and -6x divided by x is -6. So x times -6 makes -6x minus 24, and you end up with 21. So you get plus 21 over x plus 4. So my horizontal asymptote actually ends up being oblique. We're not horizontal. You can only have one or the other. Alright, and we get y equals x minus 6 for our oblique asymptote. So when I enter this in, if I'm in standard zoom, I can't actually see it. So you might want to go to zoom and hit number 3, which is zoom out, and then hit enter when it takes you back to your graph, and it'll zoom out so that you can kind of see the shape. And you should see something that goes like that, and then kind of like that, sort of. It's going to be a little spaced out differently. Alright, but then we can go to table still. Second table. And we want to start at -5 again. You could start wherever you wanted. Maybe even start at -7. -7, well, we'll add that in later. -5 goes to -32. Then we have an error at -4, which you should know you have because your vertical asymptote's at -4. -3, you got we're at 12, and then at -2, we're at 2.5. All right. Then at -1, we're at 0, which we already found earlier as one of our intercepts. And we can also put 0 at 3 because that's one of our other intercepts. And then our y-intercept, which is the next point here, is at -0.75. And then at 1, I have -0.8. And then at 2, I'm at -0.5. And at 4, I'm at 0.63. And then at 5, I'm at 1.33. Okay? So the key thing I really want to see on something like this is being able to draw your asymptotes. You have a vertical at x equals -4 and an oblique. So then you have your oblique at y. Oops. Okay. You have your oblique at y equals x minus 6. So in red again, -4. I'm going to make every other one, or every one worth 2. So every grid line here is worth 2. So then at x equals -4, we're right there. And then for our vertical asymptote, we're at y equals -6. So I'm going to draw my y-intercept at -6, because again, every grid line is worth 2 right now. And then I'm going to go up, up 1, make it 2, over 2, up 2, over 2, up 2, over 2. And so my diagonal looks something like that. Y equals x minus 6. Alright, and we have x equals -4. So there's our asymptotes. Once you've got that, you've got a majority of the information here. It's going to be on the tougher side to draw because you're getting some pretty large values. But like, if I look at this thing at like even out to out to -10. We're at -19.5. So if I change to black here at -10, which would be, let's see, 4, 6, 8, 10, we're at -20, which is almost all the way down here. So what you should see is it's going to come along this guy, shoot over, and then shoot down like that along that asymptote. Alright, and then at -3, at -3 we're way up here at 12, so 2, 4, 6, 8, 10, 12. So this one, and then at -1, we're at 0. And then at 3, we're at 0. So it looks like it comes on down here, hits those two, and then shoots on up. Okay? And so you probably have to play around with the scale on this a little bit, but for the most part, you should be able to just plot your points. As long as you have your asymptotes correct, you should be good to go.